Absolutely. It's very, very cool. This probably also has some explanatory power when it comes to why we never have a consistent upload schedule. We're just running these experiments on the dopamine receptors of our listeners. So you guys can thank us for the rush of adrenaline that you get as a result of a new upload, and the dopaminergic depression that comes when you go a week without a bit of a tangent.
Welcome back to Bit of a Tangent. It's been a while since we last released something, and I'm sorry for the delay. But today I'm thrilled to release part 3 of our series on predictive coding. We dive straight in this episode, so if the terminology seems unclear or the concepts unfamiliar, it will be worth going back to parts 1 and 2. If only to hear me confidently state that the next 3 episodes will be released in the next 3 weeks. Nevertheless, in this episode, Gianluca and I discuss the neurobiology of predictive processing, the role of dopamine in reward signaling, satisfaction and human desire, and the relation of reward to artificial intelligence and reinforcement learning. We then changed track a bit and discussed the clinical manifestations of the predictive brain, including the computational psychiatry of depression, autism-spectrum-disorder, and schizophrenia. I just want to disclaim right now that although at times in the episode we speak about the limitations of current pharmacological treatments for some of these disorders, this podcast is for informational purposes only and does not constitute medical advice. So with that, please enjoy episode 30 of Bit of a Tangent. We've so far given the basics and the understanding of how to think about the brain as a predictive engine, right, that seeks to minimize predictive error. And where I want to go now is to give some of the evidence we have that this is going on from a sort of neuroscientific and physiologic point of view. This is obviously an incomplete picture because, again, if we had a fully predictive and working model of how the brain worked, then we'd be done.
Yeah.
So this is incomplete, and lots of it is speculative, or at least is pointing the way in a way that is useful, but there are still many, many unexplained points here. So I think to get us started, we should look at maybe what predictive processing might look like in the brain, and maybe some of the evidence that the brain is doing this. And maybe the easiest place to start would be some of the sort of simple and well-known neuroscience facts about like receptive fields and how those tie into patterns of firing that we see. So I mean, the first thing is that if you look at like a retinal ganglion cell, right, they tend to exhibit this phenomenon called center surround antagonism. So if there's a stimulus right in the center of the receptive field for that neuron, then you'll get stimulation, right?
Okay.
But the same stimulus in an adjacent region, right, in the surrounding part of that receptive field, if I'm correct, that then gives you inhibition, like it dulls the response or it blunts the response.
Okay.
And sort of similarly or analogously in the cortex, I think you see a phenomenon where, let's say you've got some stimulus that's causing a region of the cortex to fire, right? But if you then take that same stimulus and use it to cause surrounding regions of the cortex to fire, then the stimulus no longer causes the first region to fire strongly. But if you then change that stimulus so that it's orthogonal in some sense, if you just imagine we're using a line here for simplicity, right? If you then make the line so that it's maximally different from what's causing the surrounding regions to fire, so in this case, literally a 90-degree rotation, then again, you get maximum firing of that cortical region.
Yeah.
And basically, what we're getting at here in a bit of a convoluted way is that the brain is probably not firing in response to the actual stimulus being passed up, but it's firing in response to prediction error, right?
Okay.
Because if you think about it, like if all the regions surrounding me in cortex are saying straight line pointing to the right, like it adds very little if I also fire and say straight line pointing to the right.
Yeah,
so
you're just overwhelming the signal.
Yeah, it adds nothing. But so me then firing, you would predict I fire much less. But then suddenly, because basically you're predicting that the line is continuous and it's straight in one region, it's going to continue to be straight in time or in space. But then if you see a line that is 90 degrees to that, right? It's like the maximum different from your current prediction. Then according to this model of how the brain works, you would predict that the brain would fire maximally in response to that. And as far as I'm aware, this is in fact what people actually see if you do this kind of experiment, is you see the brain responding to stimuli in ways that don't make sense if you're expecting the brain to be purely an engine of response to the outside world. But these results do make sense if you view the brain as predictive, as responding to predictive error.
Yeah. Okay. Interesting. Okay. Does this have something to do with where you started initially describing like the directly in and slightly outside of the receptive field? That sounded a little bit like you were starting to talk about lateral inhibition. Am I mistaken there, or?
I guess I wasn't actually going to go down that path, but it's probably worth talking about. I think okay. I was drawing more the point that parts of the neural architecture are set up so that they are, instead of being feature detectors like a classical artificial neural network, they're difference detectors, right? They're detecting when regions nearby each other are actually different, rather than like the classic edge detector that you'd get in an ANN. Here you're getting something like lines should be continuous and straight, but if suddenly it turns, that's a difference, and I want to detect that rather than detect the fact that there's like these discrete features.
Interesting. Okay, cool.
I think maybe from your point of view, right, maybe it's worth just going over like the basic idea of what a feature detector is, just to almost complete that comparison.
In terms of like a CNN, for instance.
Yeah.
Okay. So yeah, I mean, one of the areas that historically has always been tightly coupled with the neuroscience is convolutional neural networks, which are often used, a form of artificial neural network that's often used in detecting objects and images or any kind of object recognition task, or classification, segmentation, those kind of things, to do with images, generally speaking. The thing that can tell the difference between a cat and a dog in a picture, it's usually a CNN, convolutional neural network. And in essence, when you look at how the different layers of the convolutional neural network start to represent, when you look at how they start to specialize at picking up different kinds of data, different patterns, what you notice is something similar to how conventionally people have thought the human visual system was operating, where you have the earlier layers are detecting lines going in different directions. So you've got like one group of neurons that's detecting, let's say, diagonal lines that go from the bottom left to the top right. And then you've got another set that detect those going from top left to bottom right. And you've got vertical ones and horizontal ones. Or maybe you just start with vertical and horizontal, and the next layer starts doing diagonal. And then from those, you start composing more and more complex things, like you start composing the idea of an edge, and then the next idea you start composing the idea of like a curve, and deeper you go, and then you start getting into things like texture, which is where these artificial versions really come into their own with their ability to detect different things. And as you go forward, and then the last layers are like, oh, that's a dog, that's a cat, that's an ostrich, whatever it might be. And so it seems that they're looking at 4 different features, and the different layers encode those or look specially at certain features. And this tends to kind of just come out naturally as a result of training these networks, which is really interesting. But they generally get more complex and higher order, and they're composed of the earlier features the deeper into the network you go.
Yeah.
And the early research in neuroscience seemed to suggest that that biological brains were doing the same thing. So I think it was I can't remember the names of the authors, but they did a study, I think, with a cat, and so they probed part of its visual system into some like certain receptive field, and then they would show it like projections of lines going in one direction, and they would like pass another line over that, and then they would playing the output of the receptive field, and you could see like as you rotated the lines to match or be orthogonal, you would get different, like you could hear the feedback. So it was like one of those early video clips that I saw that was like, that's super, super cool, because you can see how this part of the cat's brain is just detecting horizontal lines going in this direction or whatever. But I think there's a lot more complexity added, and the more evidence we get in, the more dissimilarities we find between the two, the artificial and the biological. So I don't know if that gives a good breakdown of some of the things you were getting at.
Yeah, that's great. So I guess this is a diversion, but this does get at some of the main criticisms of sort of current generational machine learning or deep learning, where you know, we're great at building these feature extractors, but these feature extractors to me are very similar to the kind of naive bottom-up only view of the brain that we took,
exactly,
you know, as to be our sort of absurd example at the start, right? And people like Gianluca are talking more and more about these kind of generative model-based systems, and I think these are really interesting. And the kind of progress we want in artificial intelligence is more and more to be able to have systems that have an understanding of the causal structure of the world. And I mean, that for me is the direction of research that I'm most interested in watching how it pans out. Because it's one thing to, you know, make better and better convolutional nets, but it's another thing entirely to develop agents that understand something deep about the structure of the world, not just as feature detectors, but by being able to predict that structure from their own model and then compare that prediction to the incoming sense data, whatever form that's in.
Exactly. And I think a key illustrative example here is the adversarial attacks that you can perform on a convolutional neural network, right? I think some people would have seen there are examples where you can take like a picture of a whale and you can overlay like a few different like pixels of noise that's imperceptible to a human. You can't tell the difference between the two images, but suddenly the CNN goes from classifying it as a whale to classifying it as a peacock. Right? Something obviously wrong. And humans are like not fooled at all. We don't even notice the little pixels of noise. But if you've deliberately designed them to fool the bottom-up approach that these CNNs take, then it can be just so obviously wrong as to be useless, right? Worse than useless. It's actively wrong, right?
Yeah. So the next sort of like really interesting experiment, and that I think is useful to bring in here when we talk about predictive processing in the brain, is also an experiment whose results I found after I first learned about it were sort of revolutionary, I think, in terms of how you think about your life. And this is another example, sort of like we were talking about earlier with the bullshit notions of The Secret and that kind of thing, but where you actually find them somewhat redeemed in truly scientific notions of expectation and sensory data sampling. And so the experiment goes, right? You are trying to look at how the brain responds to reward, right? And particularly unexpected reward. And so the experimental setup is you have some animal, maybe a mouse, and you are monitoring the amount of firing in dopamine releasing neurons in its brain, right? And at first, obviously, you just have the animal, and if you just gave it a reward, right? So a piece of food or something, you see an increase in the amount of dopamine release, right? And so this is where the sort of naive hypothesis comes from, where people say, oh, dopamine is the signal of reward, right? Because here you got this little piece of food, and now you want to reward the animal for that, and so great, you know. And so I think a lot of sort of popular myths about dopamine and its role in addictive behavior and drugs, and even being known as like almost the happy chemical. It seems it's like that. This comes from that result, right? If you give an animal an unexpected reward, then it gets this increased amount of dopamine. But the interesting thing is that the picture is more complicated and in a very interesting and profound way, I think. So now we change the setup a bit. So now what we're going to do is we're going to give a cue, right, for that reward. Okay, so the animal learns that the cue means that it's going to receive some food. And what you notice now is that the dopamine isn't released in response to actually receiving the food. Dopamine is released after the cue is seen.
Exactly.
So now that's already interesting, right? Because that's already starting to violate our intuition that it's the feel-good hormone that's giving you the reward, right? It's because otherwise, because you can see here, it's completely attached to the cue before the reward. And then once you actually get the food or whatever, dopamine's not being stimulated anymore.
Exactly. And by the way, this interestingly just ties very closely to Pavlov's dogs, if people are familiar with that example. Just this looks at actually sampling from some dopaminergic region. I think it was like in the VTA, but the idea is the same. It's a conditioned stimulus, like Pavlov ringing the bell, that then triggers the expectation of some reward.
Exactly.
In this case, like food or surprise reward. So as you were.
So if you do that, right, you give the cue and then you give the reward, you see the spike of dopamine activity right after the cue. And then
none at the reward. Yeah. It's just kind of static, yeah.
And then the interesting thing, right, is if you give the cue, but then don't give the reward, you see the dopamine being released at the time of the cue, and then you see a decrease in dopamine activity at the time when the reward was expected. Okay. And I think this has several profound implications for us as humans and also just for what we understand dopamine to be doing. Because if you look at this, it's not too difficult to convince yourself that what dopamine is actually doing is dopamine is signaling reward prediction error, right? So in the first case we took where you just received an unexpected reward, the reason you got dopamine release after that reward is because your body is trying to flag, hey, like whatever it is that you were doing that made this come about, like you got an increased reward for this, like make that happen more often, because this is this was a prediction error, right? You were predicting a certain level of reward, and then you got an extra bit, right? And so the dopamine therefore signals that you made an error, right? And so now that dopamine response becomes associated with the cue, because when the cue occurs, well, if the cue occurs stochastically and you can't predict it, then the cue itself was unpredicted. And so you're now, based on that, you're getting a dopamine release because you're about to receive some unpredicted reward. Your prediction of the world was wrong. And that's why you don't see the dopamine response in response to the actual reward being given. It's just to the cue. And then most interestingly, right, is when you then give the cue and then don't receive the reward, you still get the dopamine for the cue. And then that depression is again the kind of reward prediction error, because now where you predicted you would receive that reward, you don't. And so now you need another way to tell your body, whatever it is that you did that time, something was off, right? You've done something which you need to do less often, because now my predicted level of reward is lower than it should be, or my actual reward is lower than what I predicted, and so you receive less dopamine. And the reason I find this kind of profound is because it tells us something about how our expectations translate into our actual experience of the world, right? I mean, there's that very sort of Stoic or Buddhist sense in which sort of desire is the root of suffering or of unsatisfaction, right? And where we are chained to the world by our desires, right? And so if you think about it, right, the animal should at baseline not be expecting to get a reward. And so when it gets this cue and it's learned that this is associated with a reward, and this literally leads to a depression in its dopamine levels, right? Even though the amount of reward it was predicting before the cue was exactly that, right? It's that dependence and that feeling of entitlement in a weird anthropomorphic way that then leads to this depressed level of dopamine. And I think sort of once you look at this experiment, it's not too difficult to convince yourself that like maybe the thing that's wrong in your life is your expectations, right? Not in fact the rewards you're getting. Like it's not too difficult given some other set of circumstances to see that, you know, your life is probably pretty good right now if you have the sort of free time and bandwidth to be listening to this podcast. And yet it's just because this has now become something that you predict you will always receive, right? And now your reward prediction error is only fires when you get something over and above this. And so you're in these perpetual, very human, very almost sad loops and cycles of ever more being needed to cause more prediction error. And this is a sort of weird, well, not weird, but this is an interesting way to account for our persistent dissatisfaction with the world, I think.
Absolutely. It's very, very cool. This probably also has some explanatory power when it comes to why we never have a consistent upload schedule. You know, we're just running these experiments on the dopamine receptors of our listeners. So you guys can thank us for the rush of adrenaline that you get as a result of a new upload, and the dopaminergic depression that comes when you go a week without a bit of a tangent.
Well, I mean, I guess you're not wrong in an important sense, which is that something about
if you overanalyze
gambling,
my joke, it will fall apart. But yeah,
yeah. Well, but I mean, there's something about gambling, right? I mean, why is gambling so addictive? Well, it's something about the unpredictability of the rewards, right? Predictable rewards quickly become boring, and so there's something about this mixture of the small chance of a large positive reward, but especially the fact that the rewards are intermittent, that makes gambling particularly resonant with human reward circuitry. And that's just interesting to think about.
It's so well researched, this, because the greatest form of slot machine is social media to some extent, right? Because like social media is engineered to be the most addicting slot machine, in the sense that they're deliberately spacing out the most engaging posts with kind of meh posts, because every time you refresh or log on, it is then like you are pulling the arm of the bandit, and you're going to get something amazing some of the time, but a lot of meh things and some really horrible things. So it's the uncertainty, right? If your feed was just perfectly prioritized from best to worst, based on what they think you'll find interesting, you would pretty quickly get over it and log off. But it's that novelty and the uncertainty and the gamble of the unknown that is what makes it so engaging. And I find this experiment that was done on these mice really, really interesting, particularly because it's so tightly coupled with this notion of temporal difference learning, which is like core to a lot of the really notable reinforcement learning techniques that are used in that domain of artificial intelligence. And it's really, really good in terms of that explanatory power. So it's absolutely fascinating. In the context of predictive coding, however, I do have some parts that I'm just like unsure about here. I get why you have the dopamine releases where you have them in the first two examples, right? You've got no stimulus and then you get a reward. Well, the dopamine is going to come after the reward. Then in the second case, you've got the conditioned stimulus now. You get the dopamine then. I understand why you get that. And no dopamine with the reward. It's kind of just regular because it's predicted. Cool. Exactly. Makes perfect sense. It's the third case that confuses me a little.
Okay.
The third case is, why is it that the conditioned stimulus arrives again, but that triggers the dopamine release? Like, why is that now unexpected? And then so then I get why you get negative when there's no reward, but it's why in that third case, when you see the conditioned stimulus again, is it unexpected? Is it just because these things are totally random and like the mouse doesn't know when it's going to come at all? So
it's like, let's say you're receiving some baseline level of reward for just existing, right? And you don't know, like all you know now is that you're in an environment where once in a while some cue arises and that tells you that you're going to get a reward, but you don't know when the cue is going to be there, right? So like your best prediction, if you just have a model of this, is like, I'm going to keep receiving this current amount of reward for just existing. Then you hear the cue and you go, oh, well, I didn't expect that. But now that I expect that, right, I signal my reward prediction error because I wasn't expecting to hear the cue. Now I do. And there's the dopamine release in response to that. So I think that's why that happens.
Okay. So that makes more sense. So it's kind of like you would never be able to predict the cue. So you're never expecting it because by definition, it's the thing you can't expect. And anytime you are able to predict it, you would then just be chaining that onto some other thing that you can't predict. And so the stimulus just goes like sort of 1 degree back.
Exactly.
If instead of it being, it's like the sound of the ice cream truck. It's like if it were super reliable on a Wednesday at 3 p.m., well, then actually the stimulus would just be looking at the calendar and seeing what day of the week it is,
right?
Not the sound of the ice cream truck.
Yeah, exactly. So I think what becomes interesting then about predictive processing is that it gives us a lens. So basically what we've gotten by adopting this model is a few new parameters that we can use to talk about the world, right? And you can start to imagine how deranging each or any or multiple of these parameters might lead to a sort of derangement of brain function, right? And the levers we've kind of got at this point are the sort of strength of our priors, the strength of, as in the top-down model, so how seriously we take that. We've got the strength of the bottom-up model, so how much are we relying on our bottom-up sensory perception, right? Then we've got maybe the point at which they're integrated, so are we doing a good job of reconciling the two and choosing new, better-fitting models? And then we've also got the variable to play with of precision. So like how precise do we think our estimates of the uncertainty are, or how precise is the sensory data we're receiving? And what I think we should maybe go into now is to walk through possibly depression, schizophrenia, and autism, and maybe just a glimpse at some of the hints that we've got that this is a good theory for explaining those. And what I'll just say before we get into that is Scott Alexander from Slate Star Codex has some really, really excellent blog posts on this topic. And so we'll make sure to link to that. But we'll do our best to sort of summarize some of his main points here. And but definitely check those out.
Awesome.
So as we said, we've got these new levers to play with, right? New parts of our model that we can use to kind of make predictions about brain states that we'll find in the world. And a fairly intuitive one, I think, is in depression. So if you think about the symptoms of depression, right, there's obviously low mood and suicidal thoughts, but there's another set which have always been maybe a little bit more difficult to make sense of, right? I mean, these are the sort of amotivational cluster of symptoms that you get where people with depression don't feel like doing anything, right? I mean, some say that it seems as if they just rather wouldn't get out of bed in the morning. In fact, depressed people, I believe, also move slower, right? There's a motor component to it as well. And so like purely explanations of depression, maybe of the sort of classical kind, where you posit some derangement in the neurotransmitters that is not allowing you to feel happiness, those don't seem to fully explain why you also have, you know, this other cluster where people are also not maybe moving around as much, right? And so what you could say maybe from a predictive processing point of view is maybe depression looks a little bit like having really low confidence in your predictions. So you could imagine someone whose certainty about their top-down predictions is lower, right? And so what that would look like is like a general underconfidence in like brain states and in ability. So just on the movement point of view, right? If you were perpetually underconfident in movement, that means that you would always be looking to sample more movement data rather than making sort of brisk, confident, well-informed limb movements. Okay. So the underconfidence in neural predictions maybe makes sense of the feeling that nothing will go right? Sort of depressed feeling that all your that things won't get any better, right? Or maybe more concretely, the sense in which you would rather sort of stay in and do nothing because your confidence in predictions of things going well, if you were to go and do things, is lower.
Okay, so it's safer. The best way to minimize prediction error when you're very unconfident about your predictions is just to not do anything.
Exactly.
Because then your predictions you're predicting very simple things, and so that minimizes the error. If you can't clean up the signal, you just don't do anything, and then that means that you minimize the error.
Exactly. And similarly for movement, you know, if you're very confident in your movement predictions and you say, I predict my limb is over there, and you can just do it, right? But if you are like systematically underconfident in all predictions, that's like a really nice unifying principle because it both predicts the sort of cognitive symptoms of depression, but also these strange related movement ones where you're now always moving slower so that you have more time to gather evidence and correct movement mistakes because you're not actually sure of how you should be moving.
Interesting. This has quite a bit of explanatory power. It's interesting to think about. So by that model, the low levels of dopamine are a result of the fact that you're not making very many predictions that you're getting wrong. So you're very seldom having high prediction error, which means you're very seldom having variations in your dopamine level, right? So as in if you just imagine that experiment with the mice, but now you give them no stimulus and no reward, then they're kind of just chilling around doing not much, right? So there's very little dopamine change, right? So what I'm getting at here is that if the dopamine spikes and troughs are associated with high prediction error, and in a depressive state, you're just avoiding making many predictions at all to try and minimize your error, then the dopamine situation is a consequence of the depression, not the cause. In which case, most of our conventional treatments, which target like essentially either bathing the brain in something like dopamine or serotonin or preventing reuptake of those chemicals, makes no sense because you're treating the effect, not the cause. I don't know.
Treating the effect, not the... I guess... Well, I mean, the first thing to note is that, I mean, our current psychiatric treatments are, at this point, notoriously ineffective in most ways. And
like fixing a microprocessor with a hammer most of the time.
Something like that, right?
It's amazing that it sometimes actually does work, like at all.
Exactly. And I guess I actually don't know on your specific point, but more generally, right? Like it's interesting to ask, if we take this kind of model seriously, like what would a good treatment look at, right? So instead of, as you say, treating effects, like looking at treating causes, it would like be asking how could we better treat. It becomes interesting, right? Because you start to view psychiatric diseases as computational problems, and we're definitely going to get to a way in which that's, I think, very easy to understand a little bit later here. But thinking more about the brain as this abstract computational device, and then thinking about the kinds of problems that computational devices can get into, and then how we would fix that, that's like really interesting. Instead of thinking of it as a biological problem where like there's too little of neurotransmitter X, give more neurotransmitter X, we say neurotransmitter X, or let's just take dopamine, it signals prediction error. Here's a disease where we've got a problem with our prediction error. Can we find a way to increase prediction error rather than saying, can we find a way to increase dopamine? Yeah,
exactly.
That was,
right.
Yeah.
Because I mean, that traditional sort of dogma of, all of these kind of psychiatric conditions are caused, well, many of them are caused by some kind of neurochemical imbalance, especially things like major depressive disorders or bipolar disorders. Like, there's a chemical imbalance in the brain. And so the solution is just to fix the imbalance by adding more chemicals in or removing some or limiting the rates of some.
Yeah.
Right. But if that's actually the effect and not the cause, right? If that is what happens as a result of some underlying cause, as the predictive processing seems to suggest to us, then it means that we're treating the wrong thing, right? It's like, oh man, what would be a good example? Anyway, but you get the point I'm making, is that it completely flips this old narrative of, things that cause depression are just an imbalance in neurochemistry, and so we just fix the balance by adding more chemicals or removing some chemicals.
Yeah. Instead of balances on a chemical level, it's kind of like thinking. It's a beautiful illustration of the difference between like the computational level and the biological implementations of that computation, right? Because what we want to do is fix the abstract computational problem that's going on, in some sense, without caring too much about the biology that underpins it. We only care about it insofar as that helps us address the computation. But I like this because the imbalance narrative is just obviously overly simplistic. And more and more as a species, I guess my hope is that with brain research, we get to this computational level, the algorithmic understanding of things. So another sort of interesting explanation I've heard proposed this time for autism is that autism reflects a pathologically high precision in our in prediction errors. So what that might look like, right, is, so right now you're sitting in your chair, right? And there are many things which have been going on in the background which your top-down prediction has explained away, right? So like your clothes are on your skin, your tongue is sitting in your mouth, there's some background white noise, and none of that you're paying attention to because your top-down prediction is there'll be clothes on skin and there will be white noise and there will be my tongue in my mouth. And even though all of those things are changing in time, right? There's the dynamic component to each of them, right? I mean, there's no two parts of your shirt are touching you in the exact same place, right? But what's happened is that your top-down prediction has a sufficiently broad sort of confidence interval that says, if my clothes touch my skin here or 1 millimeter to the left, that's still the same phenomenon. Like you don't have to propagate any error upward because I've predicted that too, right? You're predicting a whole class of sensory experiences because your confidence interval over where you're going to be touched is sufficiently wide that you expect it in a general region, right? And so the claim is that autistic people, this is not the case. And in fact, being touched here by my clothes and being touched 1 millimeter to the left is not is distinct. And so they're like, let's say you're sitting perfectly still. What this would feel like is you're sitting perfectly still and now you've predicted away all the error. But now just in the natural course of breathing, right, you shift your clothes a bit. And in you and I, nothing happens, right? Our predictive model also explains away that. So we don't even register that our clothes have shifted. But if you have a sufficiently high precision prediction on that, then you do notice the 1 millimeter shift. And so you propagate that up as error. And of course, because our brains are these machines which we're positing seek to minimize error, that would be like highly distracting.
Yeah.
And so the claim is that like this sort of routine seeking and love of almost order, right, that you see in autism is a consequence of the need to minimize error in a world where any deviation requires an entirely new model to be recruited to minimize that error. Whereas we have these more general models that do a good job of explaining away much broader classes of error, if I can say it like that.
That is super interesting. That would also be able to account for the fact that autism seems to fall along some kind of spectrum, right? You get very, very severe cases, but you also get very, very mild, almost imperceptibly mild cases. And there's a lot of research into sort of quantifying the extent of the case, right? And so that would make sense as well. Like you can have it being a continuum because you're just varying the amount of precision in predictions, right? And so it's a continuous input, so you can get a continuous output of different kinds of actions and behaviors. It would also make sense where you can have people who are more susceptible to environmental like stimulus, right? Like they can be very like sensitive to the environment, and so like being in a very noisy place is uncomfortable and chaotic, and that harkens back to this idea of wanting to have quiet and order and structure in one's life and routine. So that's really interesting because it doesn't just explain the most extreme cases, that it explains how you can have mild cases and everything sort of in between. And now I'm almost getting to the point where I'm like cautious because, anything that has too much explanatory power is dangerous. So it's like, what does this not predict? I'm almost starting to go, hey, where does this fall apart, and is that useful and informative?
Yeah, and there's definitely a useful discussion to be had on limitations of this kind of theory. And like all sort of fields in academia, the internal debates are just as vicious as the sort of external ones. So much as people can't seem to agree whether predictive processing is right amongst other competing theories, within predictive processing, the amount of disagreement about the sort of very minute seeming details is also like right up there.
Yeah, it definitely does have some interesting ideas. Okay.
So another interesting point just on the autism story or explanation is it also accounts for another sort of common behavior that's seen in autistic people, which is the sort of like repetitive movements, right? Like stimulation,
okay.
Right? Where, or as well, like the need for like pressure, like physical pressure on the body, right? So both of these are an instance where like what feels really good is something where it's really easy to predict because it's like a strong stimulus. So like if you think about like those repetitive stimulation movements, or like sometimes called stimming, like they're really easy to predict because they're forceful. And so like you can just make the very large, like as in like higher confidence interval that like my limb will be moving with a lot of velocity right now. And it's going to be moving back and forth rhythmically. So that's really easy to predict, right? It would be kind of like completing the picture of a sine wave. It's just kind of obvious.
Yeah. Okay.
And so by doing that, you're again, like the reason it's so soothing, this story would say, is because you're removing the fundamental computational problem, which is the fact that like you otherwise suffer from much more prediction on you otherwise suffer from this feeling of always having too high a precision on your error signals, and therefore forcing you to always change models, which feels very disruptive. Whereas now with like the very strong stimulation, it's in some sense easier to predict, and so you don't have to change the model because you are yourself generating the model and then generating the actions which always confirm it.
Right. So this then sort of makes me feel like we should run the experiment or ask if we have running the experiment.
Yeah. And see, I mean, so I don't actually know the answer in that specific case, but what I really like about your point is that like any sufficiently good theory should give new predictions. And what I really love about this is, from like just the simple step, right, of translating some already observed neural phenomena, right, diseases, by then translating them into predictive processing, we then derive predictions for what else should be going on in the brain, which seem testable, at least in principle. And that's super interesting. And of course, the complications will come in if we then don't observe that. And then we say, well, does that refute it, or does that refute what we thought dopamine was doing? Like,
like is dopamine actually then not pleasurable, right? Because otherwise you'd imagine that just being surprised and discovering new things all the time would feel super pleasurable. So either, like from a naive perspective, either dopamine doesn't actually feel pleasurable, or maybe most of things are just negative predictions. So it's the absence of dopamine, whereas it's only positive prediction where you're pleasantly surprised that you get dopamine. Otherwise you get negative dopamine, right? So maybe it does feel pleasurable, but for most of their experience, people who fall on the autism spectrum are actually having this negative, like this depletion of dopamine, because they're having prediction error, but it's always in a negative direction, let's say.
So I guess the thing to flag there is, and again, this is just one of those limitations, but so remember when we spoke about dopamine, we were talking more about reward prediction error. So I was using that. So that, whereas here, this would be prediction about like the state of
generals.
Well, it could be anything, but like maybe the prediction about joint position sense, which doesn't have to be encoded in dopamine, right? So there's not just one way to encode prediction and prediction error, I don't think, in the brain.
Gotcha.
And so like I think in the case of reward, where we have an agent taking actions, we use dopamine, and maybe in combination with other things. But like in general, for like cells trying to predict and then send error from one layer to another, I don't think that necessarily has to be dopamine. And that's why you can decouple the like positive emotional valence that's associated with dopamine.
That's interesting. Okay, so we need to definitely keep distinct the mechanisms by which these things may be acting and the conceptual level that overarches everything else, right? It might be dopamine here, it might be serotonin there, it might be oxytocin, whatever.
It might even just be and
or just straight up electrical signal. Yeah.
Exactly. And then the last thing I wanted to mention just briefly, I mean, and this really has been a bit of a short tour of these pathologies, and that's as much a reflection of just the limits of what I know and how much I can say.
And also what is known, I guess.
It's super more speculative.
Yeah.
But a really interesting one is schizophrenia, right? So if you think about like the phenomenology of schizophrenia, what you've got, or even just the symptomatology, right? You have people who have delusions, right? These are like fixed false beliefs, right? And this is coupled with definitely like motor changes. This is coupled with, actually, let's stick with the delusions, and then we can see if we can make sense of that as like the big cluster that happens in schizophrenia. So one thing that schizophrenic people are quite prone to are delusions of reference. And this is basically the feeling that like some otherwise like insignificant seeming event in the world is directly related to you, right? So this might mean like a newspaper article that is really, it's talking about climate change somewhere in Bhutan. And you read this and you're convinced that this is somehow like a secret message meant for you, right? And I mean, then you can get like a persecutory part to that where you then believe that not only is it like in reference to you, but it's also somehow a threat, right? Or it's someone conspiring against you. So I mean, this is an odd psychological phenomenon. And the theory goes that what happens in schizophrenia is the role of the bottom-up part of this model starts to overwhelm the ability for top-down models to explain it. Okay. So we're putting more weight on the bottom-up part, and it's not snapping into a well-defined top-down model that explains the world. So what that might look like is here's all the normal sensory experience that you're just predicting well with your top-down model, but now your top-down model is weak and fails to predict something, right? So obviously what we've said for this whole episode is that when you fail to predict something, you send a big shot of prediction error, right? And prediction error is like by definition something that is salient in the environment, right? But if you send a big shot of prediction error about something that is otherwise completely normal, right? Like just let's say completely randomly, you send this big shot of prediction error when you are reading or watching a television advert that everything else seems normal about. Now you need to do a job of explaining what was the prediction error. And maybe what that seems like is, oh, there's something special about this. Like there's something here that is otherwise unexplained. And so you get into a point where because you are not snapping your expectations into a like well-defined cognitive schema, right? Like this nice prior belief, you then are basically reacting to more noise in the input signal, right? Like the noisy data is now throwing errors all the time, and you're left trying to explain what that error is. Whereas for someone else who is neurotypical, that person is just brushing that off as noise because their top-down model is strong enough to explain away the noise as just that. And the interesting thing is this has like a little bit of experimental confirmation in the sense that I know that if you do experiments with neurotypical and schizophrenic subjects where they have to like react to like visual pattern matching, right? So let's say you've got some lights moving across a screen, right? In the case of the lights moving in like a predictable way, like let's say they're following, I think in the experiment it was like they were following the path of an aircraft, right? Neurotypical people do a really good job of just using obviously some top-down model of how aircraft move to like predict where the lights go, right? And schizophrenic people actually do worse, I believe, right? And I get you can model that as they are not deploying a good model of the world that helps them just predict this motion. But something really interesting happens if you then change the pattern of movement so that it's much more random. So you either inject more noise or you make it behave atypically, which would mean that like neurotypical people's models should fail, right? And if you then look at this, schizophrenic people now outperform neurotypical people in predicting the motion of these lights. And you say, well, what would make sense of that? And if you think about it a little bit, you can say, well, since we know their top-down models are weaker in some sense, right? They're not reacting fully. That means that they're relying more on bottom-up information, which means that they're literally like, you could say almost paying more attention to the actual state of things, which means that they are learning more or using better the information that's there in this like randomized case. Whereas neurotypical people are just relying on their top-down model much more because that's the expectation that you should use if you expect things to follow like generally normal paths in the world. And so then the randomness is like you do a worse job of learning from it, and then you make worse predictions. So I find that like a really interesting, it's not a full confirmation, but it's an interesting study because it points at maybe this thing where you can pry apart and you can start to locate the pathology, at least in this case, somewhere at this level of paying more attention to bottom up data and less to top down models.
That's very, very cool. It also suggests that there may be some more similarities than we initially expected between conditions like depression and autism and schizophrenia. And it also suggests that a treatment or a set of treatments for those conditions would also inform us as to how we may be, like, we have this idea of, neurotypical and neuroatypical, but perhaps it's more a question of being adept or inept in certain circumstances, right? There may be times, as you've mentioned just with this example from this experiment, of for certain tasks, it might make more sense to be in tune with the noise in your senses, or to have lower confidence or higher confidence in your prediction error, right? And so if you have some kind of way of fiddling and intervening with these things, then what it actually leads to is we are able to augment minds in certain ways, where instead of having a cup of coffee, you have a vial of whatever, and maybe that, or you present yourself with certain stimulus, and that just recalibrates parts of your brain to be primed into having lower prediction error, higher prediction error, more sensitivity to signal or noise or whatever it might be, where it's less of a case of, oh, these people have some sickness and these people don't have the sickness, as it is more of a case of, how do you want this complex system to behave depending on what task you're trying to achieve, which I think is a super cool concept, because it reframes this concept of treating disease as an idea about understanding what causes variations in performance on different tasks, which leads to how can you optimize performance on different tasks, right? It takes a much more charitable view of disease, I think, and probably a more pragmatic one as well.
Yeah, definitely. I mean, it sort of makes you say, oh, okay, well, I mean, yes, there are clearly problems that you would want to fix about all of these conditions, but like there are trade-offs, and what we gain from a relatively good deployment of top-down models, we then lose our ability to learn rapidly from the world, right? And so much of just the evolution of brains and brain structures has been settling these trade-offs. Like, where do you want to sit on that landscape?
Exactly.
And so then what I wanted to then just bring in as like a last bonus, as we sort of bring this to a close, is a little bit of the research that's currently coming out on psychedelics and how they then start to affect these conditions. So, I mean, what we've done in the last little while is frame some common disorders as fundamentally computational. And it's been like fairly well hyped in the media and in various popular books, like How to Change Your Mind by Michael Pollan, right? That psychedelics and compounds like them seem to have much promise in treating disorders like depression, right? And there was an interesting paper and then a blog post by Scott Alexander as well, that the paper was by Carl Friston and Robin Carhart Harris, that basically says, well, if these diseases are computational, then maybe this purported cure or at least alleviator is also in some sense computational, right?
Interesting. Okay.
And so what they imagine, right, is that, like, how you can visualize a loss function for a neural network as, this high dimensional space, and what you're doing with gradient descent, right, is trying to move down the loss function and find the point of lowest loss, right?
Yeah, the misty mountaintop analogy, where you're not sure which direction to head to go downhill, but if you just generally head, if you take steps where the slope is negative, you just gradually head to the lowest point immediately around you, and you keep doing that, you'll eventually get into the lowest point overall, or you'll get stuck in a trough, in a local minimum. But in theory, you approach the general minimum point. You get down from the mountain, right?
What you can do is similarly to how you have a loss landscape, you can imagine cognitive systems as having a prediction error landscape, right? Where some points on this landscape represent having minimal error, right? So your world model is really good and it explains away most of your sensory input. And then there are points on this which are are really bad, right? And you have high error. And like loss landscapes in neural networks, where there are local minima and global minima as well, these landscapes presumably also have local minima, right? And the fundamental property of that local minimum being that, like, once you are in it, any movement, at least for a little while, makes your error worse, right? Because to get out of it, you'd have to make your error go up for a little while before you could maybe get down to the global minimum, which is lower overall, but locally you'll be increasing your error for a little while. And so what they then say in this paper is maybe, like, depression, for example, is in some way getting stuck in a local minimum of prediction error. So maybe you are predicting something, or what we said earlier, right? You have like very low confidence in your predictions. And so you're stuck in this local minima where the way in which you predict things about the world, right, that minimizes your error is this part of the landscape where the best schema or overarching way to do that you found so far is to have quite low confidence. And maybe that low confidence means that you always expect like relatively ambiguous evidence. And this is overall is the best way to minimize error that you've discovered so far, right? That the brain has discovered, right? Because this is now this computational landscape. And so then what they say might be happening when someone uses a psychedelic is roughly something like flattening that energy landscape. So you make all the minima shallower, right?
All right.
And what that would mean is it would be easier for you to hop out of that local minimum that you're stuck in, right? And then proceed down the gradient, right? That lets you find a much better local minimum somewhere else in the landscape, which minimizes prediction error better than the previous one. And so what I like about it, even though there's like quite a few problems and sticking points and technical details that need to be fleshed out there, what I think is awesome is just this notion of reconceptualizing things which feel psychological, right? Where people are always prone to explain them as, oh, psychedelics generally tend to act on serotonin 2-alpha receptors and they increase signaling here. What I like about this is we're starting to conceptualize things purely computationally. And I think that's just really interesting.
That's super cool. Yeah, because it's the equivalent of, instead of going, oh, your model is stuck in a local minimum, and so it's never going to learn to be a really good model and have quality predictions. So what do? And then you come and tell me, oh, what you need to do is you need to flip bits 14 and 24 in this register. And you're like, no, that's the mechanism. Like, it's the wrong level to be thinking about this. Think about it computationally. What do you need to do? Oh, you need to increase your step size, or you need to reset and train somewhere else and then find the better of the two, like local minima or something. We need to be speaking at the right level of abstraction. And given the fact that predictive coding suggests that talking about, having chemical imbalances is the wrong level of abstraction, and the computational one is more relevant, well, then our approaches to treatments should also be looking at the right level of abstraction. And it's like you say, it's moving to thinking of these complex structures as computations and not just as a bunch of chemicals or bits or whatever it might be.
Yeah, that's exactly it.
It's very, very cool.
Yeah, and so
amazing.
What I'll just quickly say there is, because I think I just didn't do a good job of saying where this energy landscape is coming from, but the general idea being that psychedelics are in some sense relaxing your prior beliefs, right? Because you have these top level beliefs like I should have low confidence in my predictions, right? That is itself a top level belief, and so by relaxing all prior beliefs, right, then first of all, this explains some of the phenomenology, right? Like the hallucinations, because now you're not snapping bottom-up sensory data into any coherent schema, which means you are like much more prone to these sort of like wild or fantastic sensory experiences, right? Because suddenly you are unconstrained, like anything that vaguely resembles something else in like that psychedelic state can like blend into it seamlessly, right? And people have this kind of experience. And so here, just as a quick addition, basically what the claim is that same relaxation of priors on, like, let's say, just your visual experience is also occurring at the level of beliefs. And by relaxing those belief priors, you are allowing the brain to jump into another minimum of prior belief, which is perhaps better or more conducive.
That's a really, really cool way of thinking about it. And also presumably it's having some effects along the way of increasing the sensitivity to maybe noise, right? Because like, I don't know, there's the phenomenon of people being really captivated by really small details that they would otherwise look over in nature or in like the surface or texture of something, things of that sort. And so it seems to me that that's much like what we're talking about with autism, where you've got heightened sensitivity to certain aspects of things like noise or autism and schizophrenia both had that component. So I think there it's an interesting thing how you're playing with these different variables.
Yeah, exactly right. Like the fascination with things which have become banal to your everyday way of seeing them is, again, this reflection of relaxed priors, because you are suddenly not relying on, oh, well, of course I know what that tree looks like. You're just looking at it like from this childlike place of curiosity, right? So I get that is, again, actually a useful point, because it points to the general phenomenon that's underlying.
Yeah. And that's the part that also I think ties into mindfulness practice in some way, right? Like mindfulness practice could be viewed, one way of looking at it would be as merely observing the input stream in detail without applying the top-down processing to put it into context, right? You're just paying attention to the breath or the things that fleet through your consciousness, as opposed to trying to classify everything as part of the model and judging it and organizing it, right? So it's purely just allowing perception of the bottom up and not enforcing the top down. It would be maybe one way of looking at it, which I think is interesting.
Yeah, you're trying to pay more and more attention to sensory phenomena and actually see them, instead of allowing your everyday kind of discursive mind to just predict away the breath or something like that. And so you're paying more attention.
That's super cool.
Yeah.
Super, super cool.
And then I guess the last thing I'll say, and then I think we'll wrap this up, is I sort of promised that we would do a brief discussion of just the reformulation of this in terms of free energy and the free energy minimization principle, which is sort of largely the brainchild of Carl Friston. And
Friston free energy.
There we
go.
I
feel like we need a jingle for that. Yeah.
Yeah, Friston free energy. So, I mean, the basic idea is it's related to the physics idea, where the free energy in the system is the part of the system that you can use to do useful work, right? And so the idea is that, first of all, free energy principles, as I understand it, are just much more general than pure predictive processing. So like, Friston sort of takes this to the extreme, where like everything in biology is in some sense trying to minimize a free energy. And here the free energy minimization means that you are doing the maximum amount of work given your current sensory data. And that kind of makes sense, right? So if you are doing if your world model is accurate, right, and you're predicting away everything that can be predicted away, then there's no more free energy left. Like, you've got all the useful information that you can. Whereas if there's still free energy left, that means there's some part of the incoming sensory stream that you're not using to its maximal extent. I think that's the kind of intuition behind it. But I think there's much more to the theory, and maybe one day, years in the future, we will sit down and talk about that.
Nice. Okay, so you realized as soon as you brought out your the much anticipated predictive coding episode, now you need something else to tease people about going forward, right? So
that's it.
It's now it's free energy.
No, I'm not making that commitment, but we will find something else worth teasing about. Definitely.
Awesome. Right, well, that's been really, really cool. I think this is we've almost gone all over the place with this, but it all falls into these overarching ideas, and predictive coding has been, I'm so glad we dug into this, because this is just really, it's given me a lot to think about, and it's been really, really interesting on a number of levels.
Yeah.
So thank you for bringing all your research and things like that, and all the reading and personal learning that you've been doing on this over many, many months now, to the conversation, because it's been awesome for me to learn from you, and to sort of get the distillation of some of the core ideas for this. And just on that note, are there any resources or recommendations that you have for people who want to know a bit more about this, things that you encountered along the way that were really informative? I think you mentioned Slate Star Codex, and there are a series of posts on there in terms of the pathologies, but are there other sources that you would recommend people check out to learn a bit more?
Yeah, so the best place to start is probably Scott Alexander's book review on Slate Star Codex of a book called Surfing Uncertainty. which is, this, like, I think it's the only book length sort of treatment of all of these ideas, and it's super comprehensive and generally excellent. And I mean, that was the main resource, the book itself. So I mean, Scott's book review does a really good job of summarizing it if you don't have the time and you want to know a bit more. But if you really want to know more, you can't beat just getting a hold of the book Surfing Uncertainty by Andy Clark and giving that a read. It's excellent, and
awesome.
Yeah, it really is. And the rest of Scott's blog posts are good. But honestly, I mean, half of my motivation for doing this episode is because I never really saw anyone else. So I mean, prior to seeing the Scott blog posts, I didn't really see anyone talking about this. And I was wondering if I was just, a bit crazy, or if it really wasn't as important as it seemed to be. And then I'm glad that Scott speaks about it so much, and that he's also so entranced by the ideas. And I really do encourage anyone who's found this at all interesting to go and learn a bit more and see if there's, like, whatever it is you're involved in, see if there's a way that these ideas can generalize to your field, because I think they're like a rich fount of good theoretical ideas that are probably applicable in more than just the domain of theoretical neuroscience.
Definitely. Yeah. And I think one of the next great steps in this will be to have more experimental evidence to really drill down into what aspects are on point, which ones aren't, which ones need adjusting, and to refine the theoretical model. So I think the more people that are aware of this, the more people will be starting to experiment, both in the neuroscientific sense and also in the artificial models, because I think a lot of these ideas could lead to really interesting directions of research in AI. For instance, this idea of having an internal model just makes me think, maybe we actually want to have a GAN just generating models inside, and then you compare that with the, let's say, results of your convolutional neural networks, like sensory input, right? You're almost like simulating this with the structures that we know from AI. So I think there's a lot of cool ideas to explore there. And you did mention Gianluca, so presumably this is already something that people are looking into. And yeah, that'd be really interesting to see where all of this leads. And it's been really cool digging into it all.
Yeah, well, thank you so much for joining me. I've been
thank you.
Thoroughly enjoying just chatting about it. So
yeah, that's been great. Thanks. Until next time.
Until next time. Thank you for listening to Bit of a Tangent. If you enjoyed this episode, or indeed the entire series, let us know on Twitter @podtangent. And if you really, really enjoyed it, please share it with a friend who might enjoy it too. We massively appreciate that. And from Gianluca and I, we wish you well for the end of 2020.